All right, let's learn about rational functions. They are fractions, where the top and the bottom expressions are polynomials, and their structure leads them to have things called horizontal and vertical asymptotes. I'm going to go quickly through this because you can cover this content pretty fast. Draw a dashed line to mark the horizontal asymptote. Well, you're drawing a horizontal line, and it's drawn as I shown because the graph is leveling off as you reach the ends of the graph going toward positive infinity and negative infinity. Number 2, just to do this again, draw the horizontal asymptotes. There's the horizontal asymptote there, and this one has a horizontal asymptote about right there. As you learned earlier this year when you were learning about limits, horizontal asymptotes are determined by the highest degree term on the top and the bottom. There are 3 cases. Case number 1, the top and bottom have the same degree. In this case, the horizontal asymptote is the ratio of the coefficients, y equals a over b. In case number 2, the bottom has a higher degree. In that case, the bottom grows faster than the top, and so the overall value of the fraction approaches 0 as x takes on larger and larger positive or negative values. And case number 3, the top has a higher degree, which in this case the top grows faster than the bottom, and so the overall value of the fraction approaches positive or negative infinity. Number 4, since a horizontal asymptote is a line, it can be identified by an equation in the form y equals some number. We'll look at 5 of these right now. A, y equals 2x over x. When we're looking at these terms, the horizontal asymptote is 2 over 1, or just 2. The highest degree terms are 2x and 8x. So y equals 2 over 8, or 1/4. I'm making these easy, but that's okay. Just want you to get a sense of how these go. Y equals 1, y equals 6. Number 5. The graphs below contain vertical asymptotes. Now I just want you to draw the vertical asymptotes. So there's one, and there's one. In part B, we have 1, 2, 3 vertical asymptotes. Vertical asymptotes occur when the function is undefined, unless there is a hole in the graph. To find any vertical asymptotes, factor the top and bottom and see if any factors are repeated. These repeated factors create a hole in the graph. They create a disguised form of 1. All the remaining factors in the bottom can be set equal to 0 to find the vertical asymptotes. Vertical asymptotes are lines, so they can be identified by an equation in the form x equals some number. Write the equation for the vertical asymptote for each function below. X minus 2, make it equal 0 because nothing can be canceled in the top and the bottom. So this one has a horizontal asymptote of x equals 2. In part B, nothing can be canceled, so I set the denominator equal to 0. Whoops, that's not what I meant to do. Solve for x, x equals 8. In part C, if you factor the denominator, we actually see that there is a repeated factor in the top and the bottom. So the simplified form of this fraction is 1 over x plus 3. And now I can once again set the denominator equal to 0, and I see that I have only one vertical asymptote. The other factor that we canceled out would create a hole in the graph with an x value of 3. All right, let's move down the page. The graph of each function shown contains a hole. Using more complex language, this point is called a removable discontinuity. So fancy and lengthy. We'll just call it a hole for now. Find the coordinates of the hole for each function. Let's start by fully factoring the top and the bottom. And now we see a repeated factor, x plus 1 over x plus 1. That means we have a hole when x equals negative 1. To find the y value, just plug that into the original function. But if we look at our work, we get that it's 0 over 0 when we plug it back into the original function. That's undefined, or called indeterminate. Oh, of course it is. We forgot to remove the disguised form of 1 that is creating that undefined or indeterminate expression. So when we say we're going to find f of 1, or f of negative 1, we actually have to plug it in to the simplified form of the function, which is just f of x equals 2, when we remove the x plus 1 over x plus 1. So in this case, if we plug in negative 1 or any number, the y value is always going to be 2. So negative 1 comma 2 is the location of the hole in this graph. Moving on to the next one, let's simplify or factor first. Now since the x on the top and the bottom canceled out, then we have a hole at x equals 0. Now we're going to plug in that value into the simplified form of g of x. G of x equals 3 times x plus 1, so g of 0 equals 3 times 0 plus 1, which is just 3. So we found that 0, comma 3 is the hole in this function. Now we're not going to do a lot with the finding the holes in the rational functions, but I just want to point out that they are there. Number 8, identify the vertical asymptote of each function below. Start by fully factoring the top and the bottom. See if any repeated factors cancel out, which is where your holes are located, and then go on and set the remaining factors equal to 0 in the denominator. In part A, nothing cancels out, so we're just going to factor the bottom completely. This is how many vertical asymptotes there are. There are 3 after you have fully factored and set each factor equal to 0. Moving on to the next one, I'm going to fully factor and see if there are any holes, and then find the remaining vertical asymptotes. Here's the function fully factored, and you can see there were 2 repeated factors sets. So there's a hole at x equals negative 2 and a hole at x equals 0. H of x is completely simplified at the bottom of my work here, and so we can see that we end up having 2 vertical asymptotes, x equals negative 6 and positive 2. Number 9, identify the vertical asymptote of y equals 1 over x squared plus 1. Well, we'd want to set x squared plus 1 equal to 0. We solve for x. You get x squared equals negative 1. So x equals, what? Hold on a second. What number squared equals negative 1? Well, that would be positive or negative I. That is not real, so there are no vertical asymptotes, because that is not real. Number 10, why does the function have no vertical asymptote? Because there is no real number that will make the denominator equal 0. No real number. Number 11, for which values of b will the function y equals 1 over x squared plus b have no vertical asymptote? There will be a vertical asymptote if the denominator, x squared plus b, equals 0. If you solve for x squared, you get x squared is negative b. Well, negative b, as long as it is less than 0, that will make x squared equal a negative number. And if x squared equals a negative number, then x is imaginary. So we can think about sort of solving this. When you divide by a negative 1, you'll switch the direction of the inequality. 0 divided by negative 1 is still 0. So as long as b is something positive, the function will have no vertical asymptotes. Number 12, identify the intervals on which each function is decreasing. I'm going to highlight those in red. This is decreasing, this is decreasing, and then the other parts are increasing. Right here, you're increasing, right here, you're increasing. So I just need to write those in interval notation. The first interval is negative infinity to negative 2, and then there's a vertical asymptote. So we have to remove negative 2 from that interval, and then pick up at negative 2, comma, 0, stopping at 0, because at 0, the function is neither increasing nor decreasing. Part B, let's look at when it is decreasing. This part is decreasing, this part is decreasing, this part is decreasing, decreasing. It is all decreasing, except we do have to take out any part where the function is undefined. So negative infinity all the way to negative 4, parentheses, and then the union of that interval with negative 4 all the way to 2, and then break it, and then the union of that interval with the interval 2 to infinity. Number 13, identify the intervals on which each function in the previous scenario is concave down. Well, let's look at this part here. That's concave down. That's part of a frown. This is concave up, part of a smile. Concave down. So we want to put these two regions as being concave down, right here and right here. That's negative infinity to negative 2, and positive 2 all the way to infinity. That's part A. Part B. This part is concave down. This is concave up, concave down, and concave up. So this part's concave down, and maybe right in here could be concave down. We don't want to get caught up on how accurate we are. I want you to just estimate at this point. So the first interval of concave down is negative infinity to negative 4, and then we'll go with 0 to 2 as the other part. I just want you to start picturing when it's increasing and decreasing and when these functions are concave up and concave down. Number 14, you can sketch an approximate graph of a rational function using what you now know about asymptotes and what you have learned about first and second derivatives. Before you try to sketch an entire function, how can you determine when a rational function is increasing or decreasing without looking at its graph? Increasing is a positive slope, decreasing is a negative slope, and we find slope, or we analyze slope using the derivative. So find the derivative, figure out when it's positive or negative, and you can use a number line to do that. And number 15 is set up just to get you to practice this once. Find the intervals on which the function is increasing. We'll start by taking the derivative. This is a fraction, so we're going to use the quotient rule, and I like to say that the quotient rule is low d high minus high d low over low squared, low d high minus high d low over low squared. So here's the work for that. Now I'm going to simplify the top as much as I can. All right, that's my fully simplified derivative. To find when the function is increasing or decreasing, you need to know when it's positive or negative, and we can use a number line to set that up. But we first need to find points on our number line that we're going to mark, and those points that we mark are when the function is either 0 or undefined. So those are two different categories. Find when y prime is equal to 0. To do that, make the top equal 0. And then find when the y prime is undefined, make the bottom equal 0. Now this is my work for that. The work in blue shows that the top never equals 0, not for any real numbers, and the bottom is undefined for two different values. So when we set up our number line, we're going to mark any points where it's 0 or undefined. There are 2 in this case, and now we just plug in values into the derivative to see if the derivative is positive or negative. So I can plug in x equals negative 5, x equals 0, and x equals 3. Now in this case, we just care about whether the derivative is positive or negative. We don't care about the numerical value. So when I plug in negative 5, this value right here, x squared is negative 5 times negative 5, so that's 25. 25 times negative 2 is negative 50, and then negative 66. So I'm going to mark that that's a negative value, and then I'm going to look at the bottom. When I plug in negative 5 into the bottom expression, you get a positive value, which means that we have a negative over a positive, so y prime is negative. So it's going to be decreasing. Let's let x equal 0. When we plug in 0 into y prime, the top value is negative 16. That's negative. And the bottom number is negative 8, but it gets squared. So negative number squared is positive. So that means y prime in this interval is negative. And again, then we know that the function is going to be decreasing. Lastly, let x equal 3. When you let x equal 3, you're going to get a negative number on the top, and on the bottom you'll get a positive number, which tells us that y prime is negative, and so this region is also decreasing. Now we have 3 decreasing intervals. That means there are no intervals on which the function is increasing. So if we go back to our original sort of question here, I'll bring it down here. None. How can you determine when a rational function is concave up or down without looking at its graph? This is a second derivative question. Find the second derivative, set it equal to 0. That's where the concavity changes. And then find out when the second derivative is positive or negative to find out when it's concave up or down. So here's some outlined explanation of that. Number 17, find the intervals on which the function is concave down. Let's start by finding the derivative and then taking the second derivative. Remembering to use low d high minus high d low over low squared. This is my work for the first derivative after I've simplified it pretty much. And then I'll take the second derivative using the same thing, low d high minus high d low over low squared. Now this is some of my work, but I'm running out of space on my screen, so I'm going to slide down and continue to simplify. Now this is a huge amount of work, and I want you to just know that you're not going to be expected to do things like this often, because there's just a lot of work involved in it, and we're kind of losing track of the whole point of all this. But remember, when we found the second derivative, and in this case I've left out one little part where I can do a tiny bit of canceling, so that'll become a 3. I want to look at when is the top equal to 0 and when is the bottom equal to 0. So find when the second derivative is 0 or undefined, because both of those are values that we're going to want to put on our number line. So I'll mark both of those. At this point, there was one value that made the top equal 0, x equals 0, and two values that made the denominator equal 0, -4 and +4. This is a lot of work, and you can totally skip all this work and just listen. I could plug in x equals -5, x equals -1, x equals +1, x equals 5. At this point, you can use a calculator to find this. I don't want you to spend a lot of time on it. I'm just going to go ahead and show you the result if you were to plug these in. When x is -5, y double prime is negative. So that means it's concave down. When x is -1, y double prime is positive. So that means we're concave up right there. When x is equal to 1, y double prime is negative, so concave down. When x equals 5, y double prime is positive, so that would be concave up. Now I'm going to change those colors. All right, that's better. Now I have the concave up and down regions marked in blue. Now we were looking for when is the function concave down. So there are two regions when it's concave down, and I'll mark that here. I just want to reiterate, I used a complex example because I wanted you to see multiple regions where it's concave up or concave down. But we're going to start a lot simpler when you're looking through practice problems on your homework assignment.